All right. Happy Friday to everyone. Welcome to another edition of the F Word, programming in Fortran, of course. Today we'll be going over how to ensure stability for variable coefficient advection equation solvers, particularly for the spectra element methods. Now, a lot of the stuff we'll do, of course, has connections to finite difference methods, and let's go ahead and just dive into some of the references here so you know where I'm pulling a lot of this information from in case you want to read along and join me on this journey here. So at the top is a book from David Kopriva, absolutely excellent for learning how to do very practical stuff with spectra element methods. It's where I got started years ago. And then there are 3 separate papers that a lot of the content is coming from today, particularly the 2013 and 2014 papers, but there is some backing material from this 2009 paper from Kopriva and Gassner. So let's talk a little bit about the problem that we have. So we're kind of picking up from where we were last week. Remember, what we're trying to do is to solve a conservation law in multiple spatial dimensions and in potentially complicated geometries. So, in this picture here, you might think about in 2D, breaking apart a region of space, which would be, this square with a hole cut out in this example. And we divide this up into elements. And the way we do this with the spectra element methods is using what are called tensor product domains. So every element has logically 4 sides. But we do allow those sides to be curved. And this is what are called isoparametric elements. In other words, we can have polynomial representations of some of the grid geometry, inside of each of these elements. And the way we usually handle that is although the conservation laws we start with are posed in physical dimensions, what we do is we map each one of these elements to a reference domain. So if I were to take, for example, this element 3 here, right, and define a mapping onto a reference square that's on -1 to 1 in each direction, we can come up with some metric terms that help, they change a little bit how the equation looks. Let me actually move this over here because I didn't realize that would get blocked. There we go, that's a little bit better. And so within each element, what we essentially want to do is solve the conservation law for DG methods, which is what I'll be focusing on today and for most of this year. The discontinuous Galerkin methods solve what's called the weak form of these equations. So what we do is we multiply this conservation law by some test function that is square integrable, and we do an integration by parts once on this divergence term. And of course, after applying the mapping, which we touched on a little bit last week, we end up with something that's a little bit bizarre. So we have actually the solution we keep track of is really a Jacobian weighted solution. So it's the Jacobian of the transformation multiplied by the solution vector. The source term, same thing. It ends up having a Jacobian weight there as well. And then the flux vector that we actually calculate is what we call the contravariant projection of the flux. And what the contravariant basis vectors really are vectors that tell us the direction to move in space that get us across coordinate lines. And so that vector just needs to be rotated so we can account for those metric terms. And it's this particular integral here that ends up being a problem. Now, in continuous form, if we take the equations that we want to start modeling, usually what you want to do is make sure those equations are well posed. In other words, they have the solution of those equations are bounded. And what that means typically is like in the case of tracer advection or just an advection diffusion problem, the solution we're looking for, we want to make sure that the square of that function integrated over all of space is finite. So the problem is, though, when although we can do the proofs in analytical form before any discretization and show, okay, fine, yes, we can get stability. When we discretize, remember what we did last week is we approximate the solution and these metric terms as polynomials. And when I do that for the flux function, if I have the flux, if that depends on the solution, if that's a polynomial degree of n, these Jacobian weighted contravariant vectors are polynomial degree 2n. So the product of these is a polynomial of degree 3n, and when I do the discrete quadrature to approximate that integral, it's actually not correct. I mean, it's consistent, right? It's spectrally accurate, but it incurs an aliasing error, and we lose the ability to directly map between the discrete equations and the continuous equations. And the problem there is when you want to try to prove stability for your numerical method, all of this stuff breaks down. And so there's clever ways you can do, there's clever things you can do to get around this problem. So one of them is, last week, like I said, what we were doing is approximating those integrals with Gauss-like quadrature with polynomials of degree n, which are accurate for polynomials of 2n plus 1, or they're exact for polynomials of degree 2n plus 1. So one trick, it's called over-integration, is when we approximate this integral in the discrete form, you can just increase the number of points you're using for your quadrature and try to bring down that aliasing error, drive it down. So that's one method. It's a little bit more, it's computationally expensive because you're adding more work to do, of course. Now anything we do is going to be more work, but we want to get it right in the most efficient way possible. Now the other strategy, and this is very common in like ocean and atmospheric sciences, is what we do and not a lot of folks use spectral elements in that community, but the general idea is to overcome these kind of nonlinear or these aliasing errors that arise from like nonlinear advection, is to put in an artificial or numerical viscosity, and you'll put in like a Laplacian term. And the idea is you'll use, some type of dissipation you put in there to keep things stable. Now the problem with that approach is now you're modifying the original equations you wanted to solve, which introduces a very hard to quantify error to your problem. So it's not ideal. And the third approach is what we're actually going to talk about today, and it comes from some of these references here. In particular, if you were to take a look at this 2014 paper, we're going to be implementing some of the stuff that's written up in here, and I'll talk at a very high level about how to come up with these methods. But this is a method that essentially what we do is, rather than starting from this form of the equations to generate the weak form, we do something pretty clever to write an equivalent form of the divergence. So we get one that's based on doing a chain rule for the divergence, and one that's in its current form, and we just average the two so that the aliasing errors cancel out. So I'll kind of walk through the gist of how that works, and we're going to do it just in 1D to keep things simple. But what's nice, because we do tensor product methods, this stuff translates to 2D and to 3D as well. But we'll start with 1D because that's fairly easy. And so what we're looking at here is just the one-way advection equation. Well, I guess it could be two-way because now we have variable coefficient advection. And the domain is from 0 to L. And on the left-hand side, over at 0, we have a prescribed solution for for S, it's just GL of t, and on the right side of the domain, it's GR of t, and then of course we have an initial condition. So to illustrate to you how this works, we got to start with a bit of what I mean by a well-posed problem. And what we're trying to do, like I said before, very briefly, was essentially, if a solution follows that PDE, if it's supposed to evolve according to this PDE, we need to see if we can put a bound on the square of that function later in time. Because if we can do that, we can basically say, okay, we know that the ending solution is going to be square integrable, so we should be able to get something meaningful out of this PDE. All right, so how do we do that? So again, what we're looking for is, how does S squared look like? What does that look like in relation to the initial condition at a later time? And that magnitude is going to be the integral from 0 to L, so the integral over all of space of S squared dx. We want to know how that quantity evolves over time, because if I can show, again, if I could show that that's finite, the solution is square integrable, I've got a well-posed problem. And of course, what we eventually want to do is take that. So now I know the continuous equations I'm starting from are well posed. When I discretize, I want to make sure the discrete system is well posed. And as long as I can keep that property in my discrete system, I've got a provably stable numerical method. Okay. So like we did last week, I do need to introduce the inner product. So remember the inner product, I'm going to denote it with these carets. So if I have two functions u and v that are square integrable, I can write that as the integral here from 0 to L of u times v dx. So of course this energy is really just the inner product of S with itself. That's just one definition of the magnitude there. Okay, so what we're going to do is we're actually going to take an inner product of the PDE with S, with the solution, and then we'll come up with a way to put bounds on the energy. And in the process, we'll keep track of some of the steps that are required to make this happen so that we can try to mimic that in the discrete form. Okay, so let's go ahead and get started there. So if I were to take the equation I start with and I take an inner product with S, I have that first term ds dt, inner product with S. Then I have plus u s. This is, of course, all with the derivative with respect to x. Inner product there, and then on the right-hand side I have this b, inner product with s. So we need to look at two forms of this equation in order to get an energy bound. This is just part of the proof of coming up with that energy bound. So the first thing we're going to do is do an integration by parts on this flux term. So let's take a look at what that looks like. So I'm just going to carry down this first term, ds dt, inner product with s. So remember what we do here is we just take the derivative. What we end up doing with an integration by parts is we get this whole thing evaluated at the boundaries without the derivative. So I get us squared evaluated at the boundaries. So of course, you know, that symbol means we're taking the difference between us squared on the left and right side. And then we have minus inner product of us. So I've moved the derivative off of that flux term and put it onto that test function. In this case, that test function is just the solution. And that's going to still be equal to, on the right-hand side, we got b times s. So that's just one form of the equation. Let me go ahead and change colors here, because we're going to do another form of the equation where instead of doing integration by parts, we're going to do a chain rule here, because this helps us actually drop a few terms off. Again, to get a bound for our solution. So if I do chain rule, I'm still going to get ds dt, inner product with s. And if I apply a chain rule here on this usx term, what we end up having is uxs, inner product with s. That's the first one. And I get on the next one here, I get usxs. All right, and that's equal to b, inner product with s. Cool. So now we've got these two forms. What we can actually do, there's a couple things here to recognize. So we're going to simplify a few things. One, let me get the laser pointer here. So this term here, if we were to write that out, ds dt, inner product with s, that's going to be 0 to L, ds dt s times dx, or we're integrating over x, and we can do a little bit of, again, some chain rule here. We get s squared on 2t dx, and then because my domain boundaries are not moving, I can pull that time derivative outside of the integral. So I got partial derivative with respect to time. Actually, it's going to be an absolute derivative because we've integrated out all the x components here. So it's d by dt of integral 0 to L s squared on 2 dx. I'm going to pull that factor of a half out, so I get 1/2 d by dt magnitude of s squared. So now what I've got is an equation that can tell me how the energy of the solution evolves over time. That's really what I wanted. So all right, we're heading in the right direction. So if I have that on both terms here, what I can actually do, I can add these two forms together. So this one, so the one where we did integration by parts and the one where we did chain rule together, we can add these two together, and it shouldn't take much convincing that these two are the same, but I'll do it anyways. So us, so put a little break there, USSX is going to be the integral 0 to L USSX dx, right? And we have the other term, let's go ahead and change colors again. We have USX times S right? 0 to L. I get u sx times s dx. And I mean, you could see right away, because, you know, multiplicate a times b is b times a. Thank God for that. These two are actually the same thing. So if I add these two, what I can get to have happen is this term here cancels with that term if I add the two together. And so a key part of this proof is to have some type of way to cancel off terms that have derivatives of the solution with respect to x, right? And we move that derivative back onto the velocity or the characteristic speed that things move at. Okay, so, and you'll see why that's actually very helpful here in a second. So let me go ahead and clear some space here now that we've gotten through that. What we're going to do again is add those two equations together. And if I do that, what I end up with is d by dt of the energy squared. Okay, again, remember this term here cancels with this term, so we're good there. And then what I'm left with is plus us squared. So some boundary terms, some stuff that's going to be influenced by the boundary conditions we have. And then I have things that depend on the gradient of the velocity field that's moving things around. So I get that, b, inner product with s. Okay, cool. All right. So what we're going to do here is kind of simplify things a little bit, and then we'll talk about how boundary conditions can influence the energy of the problem. Of course, the basic idea is if I inject information either from the left or the right side, I can increase or decrease the total energy of the problem, and that's totally normal. That can happen. What we don't want to have is things in the interior of the domain artificially creating energy that we don't want. Okay, so if I move things around just a little bit, you see I got an inner product with s here, inner product with s here, so I can kind of move all this stuff together. So let's see here. All right. Oh, I did not add the right-hand sides together correctly, so we've got a 2b here. Can't miss that. Let me go ahead and fix that. Sorry, I'm trying to follow along with some notes so I don't mess things up. Do my best to sketch this out beforehand. Okay, so here's where we're at so far, is we've got some equation that tells us how the energy evolves, and now what we want to do is put an upper bound on that. And what ends up happening here when we do this, so I'm going to rewrite this in a slightly different form. So you got d by dt of s squared plus us squared from 0 to L. That's going to be equal to, let's see here. So I've got 2b minus ux s with s. All right, so cool. There we go. And what I'm going to do next here is talk a little bit about the boundary conditions. So, because we have this scenario where the velocity can be going either to the left or to the right, and we need to make sure that we, if you've done method of characteristics before for PDEs, you know that things, of course, move along characteristics. So there's some stuff to work out. So to apply the boundary conditions, what we need to have is that us squared at 0, so on the left-hand side of the domain, what we need to do is if information, so let me draw a little picture here. So here's x is 0. Over here, the solution is GL of t. Okay. Yeah, thanks, Jason. Friday Night Learning, man. This is my favorite. GL of t here is going to be on the outside. That's where we're going to prescribe the solution, right? So somehow information is getting into our domain from the left side, and then we've got whatever our solution is on the right side here. So essentially, if u is positive, if u is going this way from left to right, I need to make sure that I'm grabbing GL of t. However, if it's going from right to left, I need to make sure that what I'm imposing on the boundary is actually the interior solution. Okay, so what we do, how we handle this, it's kind of clever. These guys in these conservation law fields, man, they got some really neat ideas. But what we'll do is we'll split the velocity into what we call u plus, so it's only the positive parts of u and the negative parts of u. So we got u plus at 0 and t. Of course, when we're coming in from the left, what I've actually got for the solution is GL squared, okay? Again, I'm pulling in from the left when u is positive, and then when u is negative, so we'll say u minus, this is the component of u that flows to the left, and I'll show you what those formulas look like here in a second. So it's kind of neat. And then what we get here is s squared at 0 and t. And so u plus here, what that is that is just the velocity field plus its absolute value over 2. So you can see if u is positive, what I recover is u, and the u negative is going to be u minus absolute value of u over 2. So again, if it's negative, what I end up recovering is u, right? And if it's negative here, u plus goes to 0 and vice versa. So it's kind of a clever trick to impose these boundary conditions when you have variable flow speeds. So we can do the same thing on the right-hand side of the domain. So over at x equals L, it'll look similar but not the same, right? So we got u s squared at L is equal to u plus at L at t. And again, now here when we're flowing to the right, so now we're on the other side of the domain. So here's x equals L. On the right-hand side of that boundary, we've got GR. And over here, we've got S at L and T. So when we flow to the right, we want to take S, the solution from the interior, and move it out. So we've got S, whoops, not SL. We want S at L, T squared. Plus u minus 0t. And then here, when things are flowing to the left, we're going to take the boundary condition gr squared. Okay, so that's how we're going to evaluate those boundary conditions, so we can start to simplify things a little bit. So now the thing we can do, all right, there's a couple things we can do here. So we've got some expression now for the boundary conditions that we're going to plug in. What we're going to do next is put a bound on this inner product. So one, that inner product is, remember, so we have 2b minus ux ss. All right, and that is going to be the integral 0 to L 2b minus ux. I can combine the s's to an s squared. I can actually, if I know, so b, that b function is something that's prescribed, as is the velocity field. So if I know those a priori, I can actually bound this guy by the max of 2b minus ux in that domain, so from 0 to L. So whatever those functions are, take the maximum value in that region from 0 to L, and I can just multiply that by the square energy. And the reason why I want to do that is because now I can have a simple ODE that tells me how the square energy evolves. So that's cool. All right, let's take a look at what that looks like when I put that in. So far, and what I'm going to do is I'm going to call this term here, we're going to call this guy 2 times gamma. And I'm only saying 2 times gamma, one, to be consistent with that 2014 paper from Kopriva and Gassner, in case you're following along. You guys know who've done math before, make up whatever parameter you want. Just know that that's the definition, right? So what we've got at this point is d by dt of the energy squared plus the boundary conditions, us squared at 0 and L, has got to be less than or equal to, because now I'm putting a bound on this thing, 2 gamma s squared. Okay, and so now what we'll do is we'll fill in a little bit on the boundary conditions here. So what I'm going to actually do here is I'm going to kind of gather everything that involves s squareds on the left-hand side and everything that involves g, l, and gr on the right-hand side. So I'm going to go ahead and carry down that time derivative of the total energy squared plus, and again, what I need here are, let's see, I need the solution at L. Okay. And then sorry, so that's at, that should be at L. I messed that up. All right, so we've got the solution at L from here. So I've got u plus, I'm going to go ahead and call u plus, we're going to just call that delta so I don't have to write so many things. We got u delta times s squared at L and T plus beta, which is going to be minus the u negative velocity. So I'll get these defined here in a second. S squared 0 at T, that is less than or equal to R2 gamma S squared. And then we got basically the same thing on the right hand side, except now with the GL and GR, so the things that we're imposing on the boundaries. So running out of space here a little bit, but we have delta GR squared plus beta GL squared. Okay? So if we think about this, and this is the part I'm going to kind of wash over because, one, if you've done ordinary differential equations for a semester, you know the method of integrating factors, and so you can kind of see where this is going. But essentially, if you think about s squared being your variable for your ODE, I don't care what you call it phi, what we have is d phi dt equals 2 gamma phi plus an inhomogeneous term. Okay, so if you remember integrating factors, essentially what we do is we're going to multiply by here e to the minus 2 gamma t, do basically another chain rule or an application of integration by parts essentially to come up with a bound for the energy. And this is where I'm gonna skip over a few things, but if you click on the link down in the description for the Open Collective page, there's some links up there for getting access to notes that goes through all this stuff. Of course, if you check out that paper that's referenced by Kopriva and Gassner, you'll see this stuff worked out there too. But anyways, with this, the idea being, okay, we've got this ODE that tells us how the total energy evolves. We can solve that and put a bound on the solution. Okay, so I've got s squared at some time t has got to be less than or equal to e to the 2 gamma t, the initial condition energy, we got that, plus, and there's some, again, there's some extra terms. What those extra terms come from, and I'm not going to write them all here, those extra terms are the combination of the solution evaluated at the boundary conditions and then the actual prescribed boundary conditions. But the gist of the idea here is that I have something that I can concretely bound my solution with, and we can do this in the discrete form. Now the problem is when we go to I can do this in the continuous form. The problem is when we go to the discrete form, this term here, that advection term, if the velocity is a polynomial of degree n and the solution is a polynomial of degree n, and I've got mapping terms, I've got a polynomial of degree 3n, and if you throw in the test function that we're multiplying by, it's a polynomial of degree 4n, and Gauss quadrature of degree n can't get that exact. Hence it introduces an aliasing error, and I can't use these same arguments to say that my discrete method's stable. So let's talk about how we do this in the discrete form. So part of the hitch in getting to this bound is we needed two things to happen. We needed to be able to do integration by parts, and we needed to be able to do chain rule. Okay, so the discrete operators that I use should have some of those properties maintained. And what that turns out to be for the discrete form is integration by parts becomes a summation by parts property. And it turns out in that first reference that I mentioned, actually, let me go back to that, that the DG methods with Gauss type quadrature, Gauss-Lobato or Gauss, actually preserve that property. They have a summation by parts property. So in other words, if I do an integration by parts in an analytical derivation, I know that if I do the discrete form of that integral, at least the derivative operators I'm working with preserve that property. Now the other thing is that happened here is when we applied the chain rule, we had some cancellation of terms. So essentially that's what we want to do with the discrete stability. And again, I'm not going to go over the whole proof because it takes a little bit of time. But I did put those notes together in the hopes that you guys can check it out. We could chat about it here or later or whatever. But essentially what we want to do is instead of starting from, so I'll kind of repeat this problem. We have ds dt u which depends on x, sx equals bs, okay? Instead of starting from this form to get the weak form, what we actually are going to do is a weighted sum of this conservative form and then the form with the chain rule applied. So what we'll do is we'll actually write this as alpha times usx plus 1 minus alpha. Again, as long as alpha is between 0 and 1, this is a weighted average. And what we're going to have here is usx plus uxs. And if we start in this form, and then we go through and try to come up with a stability bound, what we can do is use this free parameter alpha to actually get the aliasing errors to cancel out. That's the gist of it. So I'll walk through the first couple steps here, because I do want to also highlight what ends up happening here is we have to choose what's called a Riemann solver that's appropriate for the problem to also maintain stability. Because without a good Riemann solver, this all goes to garbage. Okay. So enough rambling. Again, we're going to do the weak form here. So what we do to get the weak form is we multiply by a test function on both sides, and we integrate over the domain. Okay. And there's the trick here is, okay, there's a few more steps, right? When we do the discretization, we take the domain, we chop it up into elements. So basically this integral from 0 to L becomes a summation of integrals k equals 1 to big K. Let's call it xk up to xk plus 1, right? Dx, fine. And so basically we're going to, again, divide that domain up into smaller elements, break up those integrals into individual integrals, and then map each of those elements to a reference element. Now the other thing we're going to do here is the conservative form, we're going to do a integration by parts. And then on the term with, let's see, which one is it going to be here? It's going to be the term with the, I want to say it's going to be the term with this derivative here. We're going to do an integration by parts on as well to move that derivative off of that particular term. Okay. So what happens when we do this? Well, I don't want to go too deep into these notes because this actually gets pretty lengthy here, but I do want to show you where we end up. So in inner product notation, when we get there to the other side, we have the grid spacing for each element on 2. We have the solution time derivative, so that dot there is denoting a time derivative. We have the test function. So that's an inner product there. As before, we get the flux at the boundary. So that flux is, again, u times the solution. Differenced at the boundaries of each element. We still have that alpha comes down because we've done an integration by parts on the conservative term here. So that's where we're at. We have u times s times d phi dc, where c is that computational coordinate. So remember, we've mapped from physical space to computational space. We also have now this 1 minus alpha. I'm going to open up some brackets here because now we've got an inner product of the the spatial derivative of the velocity field times s with the test function minus s, and we combine now u in the test function with derivative with respect to the computational coordinate. And on the right hand side we got the element spacing b s phi. So that's the weak form. Now there's a few more steps, and now if you tuned in last week, you know what those are. Essentially what we're going to do is replace the solution, the flux, and the velocity, this b function, with polynomials of degree n. We're going to change these continuous inner products to discrete inner products using Gauss type quadrature. So essentially we've moved from all square integrable functions to just polynomials of degree n, and we're going to work a few things out. So not a whole lot changes. Oh, right, the last one here is this flux. What we actually do is we replace that with an approximate flux, because what happens when you have, so here's an element boundary. So over here is element k, over here is element k plus 1. You might have the solution over here might look like this. So this is sk, and then over here the solution might be sk plus 1. And you have this jump discontinuity between the two solutions, right? And what the Riemann solver is supposed to do, or the approximate flux that we calculate, is it says, okay, I've got a left state and a right state that differ, and I know the velocity field, so I know which direction information is supposed to propagate. The Riemann solver essentially sorts that out, all right? And in most cases, it's an approximate Riemann solver. It's not exact. But the idea is we want to choose that particular function to maintain stability. Okay, so that's the gist there, and where this does end up after that point. I'll put this up at the very, very top so you can see where we're at, because we've got a few more steps to prove discrete stability. And again, I'm going to just kind of high-level approach this. All right, so what we got here is we're going to keep that delta xk, so the width of each element. I'm going to use capital S, so with serifs, that's our polynomial representation, so it's our polynomial approximation of this function, phi, and then the inner product is going to have that subscript n to denote that this is a discrete Gauss-like inner product. Alpha, we've got our flux, d phi dxc, discrete inner product. I've also got a couple things here. I'm going to have to move this on the next line. So we got plus 1 minus alpha. Okay, open these brackets up, and I have got the inner product of the interpolant of du dxc and s. So this is an aliasing error that we're purposefully incurring, because remember, u is a polynomial degree n, s is a polynomial degree n, and I'm going to restrict that to be a polynomial degree n, when in fact it's actually a polynomial of degree 2n. All right, so we've got that, and that's the inner product with phi n. Again, because we're doing discrete quadrature, then we have s, and then we have I n. What's left here? We have of u and phi, n, and then on the right-hand side, that's where I'm going to move my Riemann flux. It's going to be on the right-hand side here. Whoops, did not mean to skip ahead. So that's going to all equal minus the Riemann flux. I'll denote the Riemann flux, so an approximate flux with that star. We have phi minus 1 to 1, and remember that minus 1 to 1 is the computational coordinates, the edge of each element. So we're just looking at the equation for each element. Delta xk onto inner product of interpolant of b times s, so b, capital B here being the interpolant of that lowercase b function with phi. Okay, so we've got the weak form, and you know that to get an energy equation, what we want to do is replace these phi's with s's, right? That's going to get us the equation we need to figure out if we can put a bound on the discrete energy that we calculate. So let's go ahead and substitute those in. Everywhere I see a phi, I'm going to go ahead and put in s. There we go. There's that guy, and then we got one more over here. Whew, we're getting there. All right. So here's the part that's actually really important. What we want to have happen is some type of cancellation to get. Remember, in the analytical derivation, what we had was a way to cancel out the derivatives of the solution with respect to space. So anything with ds dxc here is what we want to get rid of, because when we did that for our continuous problem, we were able to eventually progress to an energy bound. So why not try to do that? So one thing we can do is rewrite. Let's see here. Did I get everything correct here? No, this needs to be a space derivative. I did mess that up. Okay, so that's our space derivative. So what we can do is a couple things. So remember, I did say we need to make sure that we have a discrete equivalent of integration by parts, which in that 2009 paper I mentioned at the beginning, we know that discrete Gauss-type quadrature gets a summation by parts. In other words, that integration by parts property. So there's a couple things we're going to take from the literature. So I'll put those assumptions here. So from Kopriva 2009, what we have is that the discrete form of this inner product we can actually write as fs minus 1 to 1. So in other words, we can apply essentially integration by parts, but using the discrete quadrature, which is kind of cool. So that's one thing that's going to come to our rescue here. Whoops, this needs to be the SDC. Again, remember, and just keep in mind what I'm doing here with these subscript n is denoting that we're doing discrete quadrature. Okay, so we've got that property there. And then the other thing just to keep in mind is that this term here we can write as S df dc for this problem. The interpolant of us, that is the flux function that we're working with in the discrete form. So we can use this to our advantage to get a few things to drop out. So what we're going to do is essentially apply this summation by parts formula to this term here. And what we get when we do that, all right, let me make some space for us. So again, we're going to apply summation by parts to this term and move some things around. So on the left-hand side, whoops, I just killed everything, didn't I? Oh, no, I didn't. All right, so what I get on the left-hand side is this delta xk on 2 comes down. I've got, you know what, I'm just going to call this d by dt of the discrete norm of S. So this is capital S. All right, and that's on 2. Now what I end up with when I apply that summation by parts is a 1 minus 2 alpha out front, f ds dc n, and then I'm left with 1 minus alpha, and then I just have this term left over. So I've got interpolant of ucs with s inner product with respect to n, okay? And that's still all equal to the same stuff we had before, except now we've got some additional stuff for the, to account for the fact that we did a summation by parts. So we have a 1 minus alpha with the flux minus the Riemann flux, okay? And I've got S minus 1 to 1 plus, okay, and then we got our delta xk on 2, inner product interpolant of bs with s on n, okay. Whoops, there we go, inner product there. All right, getting a little sloppy. That's all right, it's Friday evening, I think that's allowable. Okay, so now here's the trick. Like I said before, you know, in our continuous form, what we wanted to do was get rid of terms that had derivatives of the solution, and turns out we can actually do that. Whoops, that is not what I wanted to do. We can do that by setting alpha equal to 1/2. If I set alpha equal to 1/2, this term's going to go away. I'm going to get a 1/2 out front here. I'm going to get a 1/2 here. Okay? And then I just am left with things involving inner products of the solution and derivatives of my velocity field. Now there's a few more steps involved in here, because now you can also see that the stability now depends on that choice in the Riemann flux. There's a lot of details to go through, but let's look at a couple next steps here, just to show you where this is heading. So hopefully you're convinced at this point that what we're doing here is actually going to get us stability. So again, I've got this 1/2 delta xk on 2 d by dt of the norm squared, okay? And now on the right-hand side, so essentially I'm just going to move everything over to that right-hand side. What I end up with is 1/2 delta xk on 2. We got 2 interpolant of n bs. So this should start looking familiar, minus interpolant n uxs with s n, and then I've got my boundary terms. So f star minus 1/2 f s at minus 1 to 1. Cool. So the deal is we could do the same thing we did before. We can put a bound on this integral here, or this discrete integral. We could do the same thing we did before. If I actually go through the quadrature, what I can say is that 2in bs minus in uxs with s is the discrete inner product is going to be less than or equal to, again, we'll do the same trick, max within 0 to L, or within that particular element that you're looking at, of 2b minus ux. And I can actually bound it by the exact b in ux rather than the interpolant, which is actually pretty nice. And then I've got the discrete norm of s squared. So we're still going to use that trick, right? So if I do that, what I'm allowed to do now is I've got less than or equal to. All right, I'm going to get rid of this guy here. I've still got that delta xk on 2. And again, I'm going to call this guy 2 gamma, because that's what it is. And I've got 2 gamma discrete norm s squared. Cool. And already you can start to see where this is going. Now that I've got an ODE for the discrete norm of s, I can actually integrate this in time using method of integrating factors and put a bound on the discrete solution. The hitch comes from actually defining a Riemann solver so that the solution doesn't grow in an unbounded way. All right, so when you go through and let's see here. So when we go and do this kind of manipulation, so doing our method of integrating factors, what we end up with, let's see here. I'm just going to go ahead and jump ahead a few pages on my notes here. What we end up with for each element is going to be 1/2 delta xk on 2 d by dt of that integrating factor e to the minus 2 gamma t, norm of s squared, again discrete norm, that's going to be less than or equal to e to the minus 2 gamma t, because we've multiplied by our integrating factor, f star minus 1/2, whoops, got a minus out front, 1/2 f times s at the boundaries, okay? And now the deal is, if I want to get the full energy norm, what I got to do is go back and add up all the contributions from all the elements. So if I put a summation out here, so I'll bring the k's back because this is the solution within element k, Riemann flux within element k. What we end up with is a, let's see here, we got 1/2 delta xk on 2 d by dt of e to the minus 2 gamma t, sum k equals 1 up to big K sk squared discrete norm, and we've got less than or equal to, again, minus e to the minus 2 gamma t, sum k equals 1 to big K. So again, we're summing over all of the elements, f Riemann at k minus at 1/2 fk sk minus 1 to 1. All right, almost there, guys. Hang in there just for a minute. What we have at this point is basically we can bound the energy, right? Of course, if you go through and do that chain rule, you can get cut and you do your integration over time. You can come up with the a function that bounds the solution energy norm. That depends on the Riemann flux. And what you do essentially is the same thing we did before, is we're going to split this term here in terms of physical boundaries, so things over at x equals 0, x equals L, and it turns out that you can actually get the same bound as you did in the continuous form, so those are okay. And again, if you check out those notes, you'll see all that stuff there. And then you end up with internal fluxes. So the big one that's a problem for us, so I'm going to go ahead and just put in here, we'll put boundary terms, so BR plus BL, and those are they turn out to be bounded by the same bounds that we found in the continuous form. And then we have interior fluxes. So this is the fluxes between elements where you might have jump discontinuities. And so this is why you have to be really careful about how you handle these. So what you have is F star, so the Riemann flux, multiplied by the jump in the solution across an element interface, minus 1/2 times the jump in FK SK. That's what this ends up working out to. So if I break apart this, summation here into, again, the physical boundary conditions, that gives me these guys here, which again were the same ones from before. And I have things that are handled by the flux imposition because we split the domain up. Okay, so all we have to do to make sure we have stability, make sure we got that, and then we've got our minus e to the minus 2 gamma t. To make sure we have stability, essentially what we need to do is ensure that these contributions, keep getting that erased rather than the laser point. These contributions here end up being less than 0. Otherwise, we have unbounded growth. And it turns out, and again, I won't go through all of these proofs here. If you're familiar with the local Lax-Friedrichs upwind Riemann solver, that ends up is a sufficient Riemann solver to guarantee that stability. Again, I encourage you to check out those notes to kind of see a lot of the details in here, but really what we're going to be getting into next is, okay, all right, I've now got somewhat of a proof I've done here. I'd say I didn't do it as much justice as some of the papers do, which again, check out those references down below. We've got essentially a formulation of basically how to calculate a flux divergence so that I get energy stability. And the question is, okay, I've got a code that does conservative form. How the heck do I modify it? All right, and that's the last thing I want to do, and then we'll dive into the code so you can kind of see how that all starts to come together. So I'm going to skip down on my notes here, and we'll talk about implementation. So what we did, right, is we started with the conservative form. We split that into 1/2 of the conservative form plus 1/2 of the chain rule form, in other words, the skew symmetric form. And what we now have for the flux divergence, aside from the Riemann solver component, is an interpolant of du dx s with a test function, which will be each of the Lagrange interpolating polynomials, minus s times the interpolant of u with the test function, dc subscript n minus, and then our original f d phi dc n. Okay, so what we had initially, so when I say I have a conservative form solver currently in self, all I have is this term. All right, so what I want to do is go into self and modify that to actually provide us these terms. And it turns out when you go through actually plugging in the interpolants and doing the discrete quadrature, what we end up with so if I were to do ds dt plus usx equals 0, if that were my equation that I start with, and then I cast it in this split form, do the integration by parts, do the discrete quadrature, yada, 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 what I end up with is delta xk on 2, and so it'll be the solution at quadrature point m inside element k, time derivative, is going to be equal to, so I'm just looking at the solution within element k, this negative sum, I equals 0 to n, 1/2 out front. I've got L prime, so this is the Lagrange interpolating polynomial, which again, if this is looking a little foreign, just check out what we did last week, and this should catch you up with what we got. We got omega I, so those quadrature weights divided by omega n, f tilde I, so again, that's just going to be u times s here, plus sm ui minus um L prime I cm. So what I have right now implemented is just this term, right? So what I essentially want to do in the code is override the flux divergence procedure, which only calculates this. What I really want to do is half of that, and then I want to add 1/2 times this term. So let's hop in the code just so you can kind of see how that's laid out. And we're going to use essentially what's called the type extension, which we have for the advection solver to build on top of that. So let me go ahead and switch screens here, and we'll kind of walk through how that's going to come together. And the idea for me showing you this is so that maybe you might feel empowered to hop into Self and start building out your own solvers. I've tried to provide a lot of a framework so that you can work with Lagrange interpolating polynomials, with Gauss type quadrature, doing these kinds of method, and of course at some point get you to the point where you can build these out yourself. All right, so let me see if I can get this right here. What I want to do is hop over there. There I am. Okay, so in the source code, what we have, and I'll go ahead and make that a little bit bigger. There's quite a few tools here, but the higher up the stack you essentially go, where you want to usually start is in this self model class. It's where we kind of stitch everything together, all the stuff that handles your mesh, MPI, GPU acceleration, interpolance, quadrature, all that stuff's handled further down, so you don't have to think about it. But if we start in that model class, let's take a look at that structure a little bit. Must be running out of space on that disk, so I saw that swap file error. So the way this is structured is we have what's called an abstract procedure for a model. And in Self, our concept of a model is really something that has a time integrator associated with it. And we have as it assumes that we have some methods to update the solution. So if I have a current solution and you tell me the tendency, right, it tells you how to get that thing to update. So so long as you define that method, right, we can actually update the solution. Let me put on the numbering here. And then you also have a method to calculate the tendency, right? So how does this thing evolve in time? And for advection, it's essentially I need to calculate divergence of u times s. I need to add in any source terms, and I've got my tendency. These are deferred in this base model class. But the reason why we've done this is so that I can provide you with time integrators and things, so you don't have to think about that. All you got to do is set how I'm going to update my solution, how I'm going to calculate tendency. Now, I've even gone one step further. I've done type extensions of model to give you a 2D model, a 3D model, a 1D model, right? With some of the things you might already need. So typically, for conservation laws, you need a solution. If you're doing like advection diffusion, for example, you might want to calculate a gradient. We've got a flux source terms. Flux divergence is something we want to fill in. And again, this tendency, the dsdt that we calculate, those are all there for you. I've also included some attributes I'll show you how to use here in a minute that allow you to, if you have a mesh created, you can create a domain decomposition if you just give me a mesh. The mesh has enough connectivity information in there for Self to figure out how to do how each MPI rank is going to take ownership of a part of that domain. And then, of course, with spectral elements, each element in that domain has some geometry, so all those mapping and metric terms. So those are all provided for you. And then I've also got some other boilerplate things that are already defined. And again, we still have some deferred routines, but I'm trying to fill in more of those gaps so that you don't have to write a lot of this boilerplate code. And what it turns out to be for doing these problems is you just need to tell me a function to calculate the source, tell me a function how to calculate the flux, and then give me a Riemann solver. If you can define those three things, you can write a model in Self. But what did I just say, just not too long ago? I've implemented conservative form of a flux divergence, and what we need to actually do is calculate a split form. Now, unfortunately, a split form depends on the characteristics of your hyperbolic system. And by characteristics, I don't mean like the attributes. I mean like the mathematical characteristics from method of characteristics. Because of that, I can't provide that for every possible model. However, I will be building out advection and some of these other base tools in case you just want to get up and running with something simple. But what we want to do is basically do a type extension of model 2D to an advection 2D class so that we can concretize source, flux, and Riemann solver. Fine, I've got that. But what we also need to do is this flux divergence, this calculate flux divergence method, we need to override it so that you can calculate the split form. All right, so let's take a look at the calculate flux divergence we have, just so again you see what I'm talking about. Let's hop down. There it is. Pretty straightforward because I've tried to build this stuff extensively. The flux, it's a class called it's a mapped vector, so it's something that's aware of one, not just the data storage layout I have, but it's also aware of the geometry in the problem you're solving, and it does take into account metric terms to calculate the conservative form of a flux. So if I were to take a look at that guy, let's see. All right, so that's a mapped vector. So if I go into let's see, yeah, MappedData. Yeah, we'll be fine here. So if I look up divergence, MappedVector 2D, you can start to see, you know, it's going to feel a little bit obfuscated, but this structure in the code is done on purpose to provide a lot of code reuse and start to really get things abstract to where we can talk about doing calculus operations and not talk about how to program a GPU. But essentially underneath the hood, you know, if you have a flag for the form that you're using, which here is self-weak DG form, it's going to do that conservative form that I was talking about. And if you keep tailing this down, eventually you'll get to the bottom of the stack, which is the Lagrange and turbulence, where all this stuff is implemented both on the host and the device. So that's the gist of it. But like I said, what we want to do, I'm going to get write errors on this system because I think I'm running out of disk space. So I'm going to hop over here to my laptop. Figured that was going to happen. So let's hop back in here. Same source code. So what I've done here is again, we're going to do a type extension on top of self model. So if I go into the advection 2D, again, now I've done, all right, type extends model 2D, so I'm building on top of it. And whenever you do a type extension of an abstract class, what you have to do is concretize any of those deferred interfaces. If you don't do it, the compiler is going to complain. So it does put those bumpers in place to help guide you in this development process. So the concretized methods we have to do are source, flux, and Riemann solver. So let me show you those to give you an idea of how this is done, and then we'll apply the same idea to doing a flux divergence. And the other thing we need to do is, you know, of course, the first time you do this, I'd highly recommend just focus on programming it for the CPU. Don't worry about programming on a GPU until you get the CPU version working. And what I'll show you today when we do the type extension of flux divergence is how to implement that on the GPU so you can repeat that process there. But essentially what the source term does, right, so all you need to do in this method is essentially provide yourself a nested loop over the elements. These are standard structures that I'm working on documenting so that you know, like, hey, if I'm in 2D, what should the ordering of my loops be so that I get good performance? You know, so like here a source term is essentially we want to evaluate the right-hand sides of the source of a tracer at each grid point. And the grid points are divided by elements at the highest level, then for each tracer variable that we're working with, and then over the quadrature points within the elements. Right? That's basically the idea. Again, the same thing with the flux. The flux is something you evaluate at each point. So you have that same do loop structure, quadruply nested loop. If you keep that ordering, you'll be good on performance, no problem. Now there's some, I'm sure you noticed there's some weird stuff going on here, so you just need to know what to fill in. And it comes down to understanding what some of those structures are. It's like a flux is a vector. And it's a mapped vector in particular, and in DG we have this concept of thinking about solutions at the interior of elements and at the boundary of elements. So you'll see, okay, I've got this, which is the model, the advection 2D model. That model has a flux associated with it, and what we want to do is fill in the interior. Now once you pick what thing you're filling in, you got to remember, since this is a GPU accelerated code, you have both host and device data. And here, since we're doing the CPU side, we'll do the host data. Now the ordering of the ordering of the arrays here, we've got the vector direction first, then the quadrature points, then the variable that it's associated with, and then the element. Now I've added for the advection model a new attribute called the velocity, right? we want to advect things around with the velocity field. We'll pull that velocity out, multiply by the solution. That's it for the flux. The Riemann solver is a bit different because the Riemann solver is not in the interior, it's over the sides of the element. And the ordering there is we loop over the elements, we loop over the element sides, and remember everything is tensor product elements, so in 1D it's a line, 2D it's a square logically, and in 3D it's going to be a cube. So what we do, and I provide these examples in the code so you get a gist of how to pull these things out. So in this module, we're going to pull up the normal vectors at the boundaries of the element. So we have the outward pointing normal, because what we actually need to calculate is the normal flux. So we get the normal velocity, right? We just take the velocity field, again, at the boundaries, multiply by n hat, and then we're going to do the local Lax-Friedrich solver. So designing the Riemann solver is a conversation, is multiple conversations that can take place over time. And I'm hoping to get to showing you how to create those basically through doing diagonalization of the linearization of your PDE that you're working with. And there's definitely a methodology there to how you create these. And then, like I said before, when you start to do these stability proofs, you can get some guidance on which ones might work for you and which ones don't. So here we're just using local Lax-Friedrich. So essentially we take the average of the flux from both sides of the element boundary, and we subtract off the absolute value of that normal flux times the jump. And so what this always gets us is the upwind flux. Pretty straightforward. Okay, but what we end up wanting to do here is essentially override that flux divergence routine. So what we end up needing to do is add a procedure. And we're going to do calculate flux divergence. Okay, and we're going to override that with calculate flux divergence advection 2D. Okay, so I'll pull up the model 2D so you can see how this is going to end up working here. So I'm not done, but if I go into self model, all right, if I go into calculate tendency for model 2D, all right, so you could see if I were to forward step my equation, right, for Euler, it's just calculate tendency, update solution, but let's take a look at that. Calculate tendency, what it's going to do is it's going to evaluate whatever your concretized source 2D function is for your extended class. It's going to evaluate the Riemann solver for your extended class. It's going to evaluate flux 2D for your extended class, etc. You get the idea. This step here is it's called reproject. Essentially what it does is it rotates the flux vector from physical coordinates to computational coordinates, and then we calculate that flux divergence. And this is the guy right here that we want to override. And the reason why we want to override is because we want to put in split form, because currently it just does conservative form. All right, all that to just give you the idea of how this all fits together. So let's go back into that advection 2D. Right, so we got calculate flux, and I've already got a typo, so cool. Yeah, I wish I could do like giveaways for catching typos for y'all, but hey, feel free to harass me in the comments if you see something I might be making a mistake on, because if you don't catch me, the compiler certainly will. All right, so what I'm going to do is go borrow this interface, so that because when you do type extensions for procedures, you need to have the exact same inputs and outputs. Otherwise, again, it's going to complain. It's a violation of the Fortran standards. So we're going to take 526 down to 535. That's going to be 9 lines. And let's go down to our source 2D. We'll put it right above there. Doesn't matter where you put it. So we're going to change this from model 2D to advection 2D. All All right, and really what I need to do at this point is kind of just go dive into the interpolation class and pull out what's going on there so we can just implement all this in one neat space. And you know, if you are interested in developing things in Self, I am absolutely looking for folks who want to help develop models and put this stuff together. So if you start something and just open up a pull request or reach out, I'm happy to help guide you through this process. But essentially what I'm going to do here, I'm going to comment this guy out. I'm going to go into the interp class and grab out that flux divergence. So, and as you get more familiar with the code, you'll start to see the naming conventions here, and you'll figure out where things are pretty quickly. I try to do my best to be very, very structured. So what we want is divergence. We want a vector divergence. 2D. All right. And there's a lot of interface stuff here to help us be able to easily provide an API so that folks can quickly switch between CPU and GPU programming. Okay, so what we're going to do is grab essentially everything down below this local line here down to the end of this end-do, and we're going to basically overwrite this in our advection module. All right, so let's see, set number. I need 1553 down to 1570. Set 17. All right. All right, so what did we say we wanted to do? So right now, like I said, I'm doing conservative form. What I need to have, whoop, this is actually strong form here, so I grabbed the wrong one. I want vector DG divergence. Okay, there we go. Now I've got my actual, so remember before with the DG term we do weak form, so it should have some boundary terms in there, which is what this is here, and then inside here is the loop over the quadrature points to do the volume term. Okay, so let's get this actually is what we want. 1595 down to, let's say, 1620, so that's 25 lines. Now we're talking. All right, so the elements, the way you pull out elements from one of the model classes is just grab the solution. You can grab solution and elem, and then we want this %solution and var. And rather than my poly, what we need to do is grab the interpolant that's associated with this solution. So that's this solution %interp. It's the interpolant associated with that guy, and we'll do the same thing here. Okay, I do need to get this accumulator. Actually, this df is the, let's go ahead and set up an accumulator variable. That'll be a little bit more friendly. So we'll do this. So again, the Riemann component is not the problem. So all this stuff down here, okay to stay. Okay, boundary terms aren't going to change here on us. But what I need to actually do, and let me pull up the notes here. So I'm already forgetting. Okay. I need to sign back in. I got kicked out of my Google Drive. Give me a second. So I need to pull up these notes here. And all right. How can I do this without messing things up? Pull that one. That didn't do anything bad. That's good. All right. So what we need, right, is we need to do 1/2 of what we did before, right? So this conservative flux term, and then what we need to do is add the solution. Actually, I have it down in 2D here. I did derive it, and I just filled it in because it's quite a bit of work to derive. What we need to do is fill in the solution at each of the quadrature points and then do some differencing of the velocity field and then multiply that by derivative matrix, so the derivative of the Lagrange interpolating polynomials. All right, so let's see if we can hash this out. Now, there's going to be another step here for the next 2 weeks. I'm essentially going to be going through validation of all this stuff, so I will just show you implementation, make sure we can compile, make sure we run. But just keep in mind, between now and next 2 weeks, I'll basically be validating all this. All right, so let's trim this down to where we're just using that iterator, or that accumulator. And we got our accumulator. All right, so wherever I see my poly, what I want to do is replace it with this solution percent interp. Let's see here. What I want to do is wherever I see my poly, I want to replace it with this percent solution percent interp. Bam, done. Okay, so I've got my DG matrix, and what I need to do is half of this guy, so 0.5. Okay, and I know these lines are getting kind of long here, but we'll deal with it for now. Okay, so that's fine. And now what I need to add to it is for the split form, I need this percent solution percent interior. I need the solution at each point. Let's see, how am I going to do this? We got host data, ij, ivar, il. Okay, and I need to multiply by the some differencing of the velocity. So what I have, again, let's take a look at this formulation. I've got u, and so this I in that summation is really this II. That's what that guy is. So wherever I see an I got to change that to II. Wherever I see an N, I need to set that to J, because that's the second spatial dimension. And then here I've got Uij. Okay. So that's what I'm going to do. I'm going to get the velocity field. So we're going to difference that velocity field. So this percent velocity, percent interior. And since I'm in the x component first, we'll do the first component to the velocity. Host data, x component. So again, that was Iij. The velocity doesn't have a variable dimension. It's just 1. Il. Okay, minus. You know, for some other programming languages, this might look cleaner, and this is also, I guess, a downside of my approach here. But you know, the first few times you implement things, especially when you're starting to go as abstract as you need to, you bury a lot of complexity. And when you go to do new things, it might show up. But all right, so I want 1, I want ij, 1 il. Okay. Oh, right, now I need to multiply by the interpolant derivative matrix, not the DG matrix. So let's see what that was called. So if I go back into the self-Lagrange, I think, yep, I have the D matrix. So that's fine. So that's what we'll do. Percent solution, percent interp. If I really were to clean this up, I might make a pointer for interp, so I'm not having to rewrite this solution percent interp over and over. Maybe I'll do that in here in a minute. So we got D matrix, and again, host data. And then for that guy, what I need is, the way I've set those up is the summation direction is always up front. I've made sure you get the transpose there correct. And then we're doing this over the first spatial dimension. Okay, so that's the first one. So what we want to do now is add. We want to do the second spatial dimension. So we'll basically copy this and we'll kind of modify it from there. So we got 1, 2, 3 to copy. So we've got that again, and then now we've got I, and then ij. So that should be, yeah, so again, let's take a look at that. So the solution, so here's the second term here that we're working on, SMN, so that's going to be our ij, u, I, this j is now our ii, so that's u, I, and then uij. Okay, great. And then we'll get our derivative matrix as iij. Phew. So, okay, I mentioned before that we don't do over integration because it introduces more computations. And certainly you can see that this one does. I added on a whole bunch of essentially multiplies, adds, subtractions to this problem, but it's certainly not as much as basically going from, n by n points up to, 5n by 5n points. It's certainly a lot less. So that should be okay. We should be good here. So that's really all it took to put in a stabilized method. Let me make sure I got all my, I think I'm missing a parentheses here. Yep, sure am. And let's give this a compile. So if you're working with self, I'm working on building out the testing infrastructure so it's a lot easier to use. I've kind of been waffling on a few ideas, but I've landed on something that seems to work pretty well. Essentially, we build Docker containers. Those Docker containers do get in the build process. Once I have those triggers running, those get turned into Singularity containers and then shipped off to Google Cloud to run on a variety of NVIDIA GPUs, on a variety of compute platforms for the CPU-only modes. And I'm trying to figure out a way to get that connected to an on-premises AMD node. So we can test on AMD GPUs as well, but we'll get there. But you can easily just use the Dockerfile that's provided in the root directory. I'll be getting this stuff merged into develop in main soon. The first time you build, it's going to take a while because it basically installs all the dependencies for self. So this is flap, JSON Fortran, FEQ parse, HDF5, HipFort, Rockham in general, so that can be kind of a pain. Okay, so let's see what we got here. So I called this, I did not fix the name in that module, so let's go fix that. Right. Those of you who code, you know what this is all about, just kind of playing whack-a-mole until all the problems go away. So what we'll do from here, again, I'm only going to check to make sure that it compiles for now, and in the next 2 weeks, like I said, I'm going to be working on the testing infrastructure to make sure that we have an easy process to check for correctness, make sure things run on a variety of hardware. But what I really wanted to show you is how you might extend this to do a GPU accelerated kernel. So this is a little bit more involved, but it's good to know. All right, so let's just make sure that's, yeah, so because we didn't have that name right, this threw an error here, and this has no type. That's interesting. Oh, I need to get those BFs defined as well. Let's take care of that. Where's that starting? Use self model. Okay, so I'm going to go ahead and give that one more compile to see if what errors I trimmed out here. The nice thing with Docker is if you're using it locally for testing, and at least building, one, you'll always have a consistent environment. So if you run into a problem, I will likely be able to reproduce it and give you a hand. The other thing is once you run through the build process at least once, as long as you don't clear out any of the intermediate layers in your local Docker daemon, the builds will just start from whatever changed, and that will usually happen right where we have a copy statement to bring in the source code. So that's always nice. Okay, cool. So that killed pretty much everything. I do need to fix the fact that I've got F in here when it really needs to be the flux function, and then we got the BF, which is the boundary flux. So let's go fix that. Not a big deal. It's just going to make this look a little bit more like spaghetti code, which the next phase from here, if you were to submit something like this, we'd work through a process to clean it up, make it a little bit more readable. So I by no means should you ever think that it should always look pretty. If your code looks like as nasty as this, that's okay. All right, so we want flux, and we want interior, and we want it on the host data. Cool. All right, where's the other one? I got another one down here. Nope, I want flux, and I want interior, and I want host data. Great, so I took care of those. Let's get these BFs. I'll definitely clean this up. This looks ugly. Ah, and I did not assign that DF on the way out here, so we'll go ahead and fix it up. Let's see, we got William here. Kind of wish the Fortran lint format feature fully working so we can lint the code. Dude, linting, so I've been using fprettify for linting as a process. So when I finish this up, I'll hop into the contributing guide and show you how that's done. But there is a tool I have with a config file that at least lints a little bit. I am totally looking forward to some of the stuff coming out of Fortran. So if you know more about that, or if you got your ear to the ground, definitely keep in touch. All right, so we got this % flux. And again, we want the boundary flux this time. So we got boundary and then host data. Oh, we get a line continuation parameter there. Let's pull this guy back. I don't know why that got all messed up. This % flux, % boundary, host data. Okay, that's looking better. Oh, I got a couple more BFs here. Let's go ahead and take care of those. Go ahead and get this stuff lined up because this is all janky. All right, BFs, that's what I want to fix. We got this % flux, % boundary, % host data, and then this % flux, % boundary, % host data, and I think I messed up Bowdnidry. Those are the kind of spelling errors that, if you're tired, are absolutely horrendous to deal with, where you just kind of switch two letters and you're wondering why the compiler can't read, and it's really yourself. I don't know if you guys do that. I certainly do quite a bit, especially as we get towards the end of the week and things are starting to wind down. All right, so now what we want to do is fill in the flux divergence, which I forgot to do. So we need this % flux divergence, interior, and again, host data. I suppose maybe it'd be better if I had like accessor routines here to kind of clean this up, and then just like, I don't know, have them as inline accessor routines so it's not incurring an overhead. I don't know. There's lots of cool things to do, but if you have ideas, that's why this code's open source, is so we can work together on these things if you so choose. All right, so we got ij, ivar, il equals df. In the end. So we use that accumulator, we pick up all this stuff in between, and we lump it into the flux divergence. Okay, I'm gonna go ahead and get rid of this comment down below. So let's make sure this compiles. If this compiles, what I wanna show you is some of the mechanics to get the GPU acceleration in a extended procedure. So this doesn't just have to happen just for flux divergence, right? You can apply this methodology to any of those source 2D, Flux, Riemann Solver, anything that you want to override, or if you want to add new subroutines to a particular class, that works too. So got a rank mismatch. Oh, yes, I do. How on earth did that happen? What time was that? 1:46. Flux, boundary, host data. Why is that one throwing a... One, two, three, four. I know what's going on. Flux is a vector. What I actually need is the boundary flux. So let me see how I did that. Divergence. Vector divergence. DG? There we go. Yep. Okay, so what I'm actually sending across is the boundary normal. That's what I need, boundary normal. Yeah, these are all things I'm working on getting documented, so you're not completely lost when this comes about. But yeah, so that reproject function that I pointed out earlier, essentially what it does is it goes through and reprojects not just the interior, but the boundary components of the vector, so that you can basically access that boundary normal. You don't need to think about which component of the boundary flux vector you need to grab. It's kind of a convenience attribute, I guess. All right, let's give that a go. And that should be the one that ends up getting filled by the Riemann solver. So let's take a look at that just while that's building. Make sure I got that right. Yeah, and I did. So the Riemann solver, here you go. I see we're filling in that boundary normal. And that's the one we end up wanting to use for those boundary terms. Yeah, it's saying 4 out of 5, which suggests the correct array is 5-dimensional. Oh yeah, definitely. Yeah, I absolutely picked up on that. Yeah, the deal is, so let me show you the mapped vectors. So let's look up vector 2D. Okay. Actually, those attributes are actually going to be defined in the abstracted classes in self-data. So the things that so the way this is built, right, is you got interpolants down at the bottom, and then those interpolants can be used to define data. So if I have data on my grid and I have an interpolant associated with it, I can do interpolation and derivative operations in computational space. Now, if I add to that a mesh and some geometry, now I can do mapped derivatives. In other words, I can actually do things in physical space at that point. And so down at the bottom end of this is the interpolants in this self-data, which are kind of at the bottom here. So you see every data object in here has it basically has an attribute for the number of variables, the number of elements. You've got an interpolant that's associated with it, and it's a pointer so that like you don't have to keep reallocating an interpolant. You can do, and I'll show you in one of the main programs we have for testing how that comes together. They've got metadata, which helps with file I/O. It's still something I'm working on integrating into the HDF5 output, but you can like set the name of the variable, a description, units, things like that. And then you can have an equation associated with it. Like, so if you've seen the FEQ parse stuff I've done, you can essentially provide a character or a string, right, that has an equation. The equation parser will actually parse that and use a reverse Polish calculator to actually evaluate that on the fly. So it's kind of neat. Right, what was I going to show you? All right, vectors, vectors. So we have, again, the interior, the boundary, what I call the ext boundary. So this is for like setting prescribed boundary conditions. Again, another convenience array for setting what the external boundary might be. This is actually something that's used for MPI, the MPI layer to handle that, and of course for handling boundary conditions. And then that boundary normal. So it's basically, if I take the vector boundary and I dot it with n hat, I get boundary normal, which is a 4-dimensional array for 2D, where I was trying to use boundary, which is, like you said, William, a 5D array. All right, let's take a look at our build here. How did we do? Looks like it got past it. So it's actually just finalizing the build of that container. Some things that need to be worked out there still. It's like at the end I have to make sure all the libg Fortran libraries are in place, otherwise you can't run any of the executables. All right, so let's kind of dive in now and talk about how to do the GPU acceleration. There's a couple ingredients here. So the easiest way to illustrate this is to dive into the Lagrange class. Whoops. All right. Let's make that a little bit smaller. I hope that's still legible. What I want to show you is a couple things. So For every CPU routine that's there, you could have a GPU counterpart. And the way you bring that in is you actually have to write your HIP kernels, since we're using HipFort, in C++, and then you use ISOC binding to bring in, to expose those C++ kernels to the program. And the structure that I prefer for this, if you're looking in the source directory for this repository, for example, like I've got self-lagrange.f90 in here. If you look underneath the HIP subdirectory, you'll see I've got a self-lagrange.cpp. So that's the associated C++ file that contains all the HIP kernels. So I've got one already started for self-advection because I needed a couple of routines already offloaded to the GPU for the advection. If you've been following this series for some time, you've probably seen some of this stuff get developed. So what we essentially need to do inside of here is provide two routines. One is the actual kernel. And so you can see this here. It's designated by this global attribute out front. And that's the guy that actually uses the HIP syntax to schedule work on a boatload of GPU threads, right? And what we do is we wrap that with I call it a wrapper, right? Because all it's supposed to do is accept in the arguments as pointers, and then launch that kernel, and using that familiar chevron syntax from the earlier CUDA language that HIP was designed to mimic, but give you the portability to go between GPUs of different vendors. So what we want to do, right, is we've now got this flux divergence routine that we customized. We don't want to use the one that's inbuilt because it's conservative form. We want split form. So essentially what I got to do is implement that split form solver in a HIP kernel, and then implement a wrapper around that, and then expose that wrapper through ISOC binding into Fortran. Now I'm going to borrow from self-Lagrange, since that's where I borrowed the CPU routine from. It would make sense to borrow from self-Lagrange for that. So what we need to do is go find that routine that's similar enough. So I want vector DG divergence 2D. Let's go ahead and we're going to basically copy this over, modify it for our particular use, and then kind of go from there. So we're going to basically code the same thing that we just did. So I got 801 down to 831. Copy that guy. Let's go into that self-advection 2D. Okay. And I paste that in. And what I'm going to do here is I'm going to call this, you know what? I'm going to be very careful because I feel like I need to be a little bit more verbose here. So the flux divergence advection 2D. Yeah, you know what? I'll leave that the same. But in the routine that I make up here, I need to make sure this is a so we want flux divergence advection 2D, and I'm going to make sure this is split form, just so I know it's split form rather than conservative form. So we'll change that name down here as well. So yeah, these names get pretty long, but you know what? Since the compiler doesn't care, it'll digest it. I'm good. I'm blocking some code here. I'm going to turn my picture off here just for a little bit so you can follow along with the code. All right, I'm still here. All right, let's make sure we get this name correct. Flux divergence advection 2D, and again, split form. And the reason why I'm kind of showing you this method of like, all right, find a routine that's similar, copy it, and then modify it for use is because for the most part, those routines, I've spent a good deal of time thinking about the data layout, the order in which things are done, how threads access data so that it's fairly well optimized. However, no one can stop you from doing your own thing, and I'm certainly not going to be upset about it. I'd love to see how other people tackle these problems. Okay, so remember the difference here with the split form method is in addition to the flux, in addition to the solution, we need the we need the velocity value. So I need to keep this flux function in so I can continue to calculate that conservative flux, but now I need to actually add in as arguments the solution. So we'll add a real solution. And if you're curious, because you might be thinking, why are you using real? That's not a type in C++. And you're right, it's not. There's a header file that allows you to toggle between double and single precision that's controlled at build time. And I use a macro called real to configure that. So we can actually do single and double precision builds depending on what you want to do. All right, so I need the solution, and I also need the velocity, okay? And so let's just mimic that here. So I'm just trying to stage everything that we need. And then once we have everything we need, we'll fill in the instructions in the GPU kernel so that we're getting things correct there. And once we have that, we'll go ahead and write the interface on the Fortran side and then put in some conditional logic that toggles between actually doing the GPU acceleration or not. Okay, I'm going to put myself back on because I'm moving up higher in the code. Hello again. Okay. So here, what I'm actually going to do is I'm going to go ahead and use an accumulator. I don't know why I wasn't doing that before, but we'll do real df loc and df loc. Again, this is a little bit more friendly on the. Let's pop this down here. It's a little bit more friendly to use a register rather than referencing something in global memory. Whoops, what I actually want is that. We're going to kind of repeat that process. I should probably go back and clean that up on the Lagrange CUDA kernels, or HIP kernels. All right, df loc. So again, we'll go ahead and do that here. So I got df loc, df loc. All right. So again, what I want to do is 0.5 times that. I believe that DG matrix already takes into account that negative sign. So actually, no, it doesn't. I know where I take it. Ignore me. All right, so we've got the conservative form. Now we need to add the split form down below. And I'm going to cheat, if you call it cheating, I suppose. Advection 2D, Flux Divergence. Okay, what I'm going to do is copy this stuff here. 1, 2, 3, 4, 5, 6, 7. And drop it in. And here's where we get to cheat a little bit. So I need this solution. And I've provided macros in a header file in that HIP directory for doing multidimensional indexing. I know it's like a C practice. I'm in C++, and this is really speaking to my ignorance of C++ programming, but I like it. It works out pretty darn well. It's very, very low overhead. You just do a little bit of integer arithmetic under the hood to calculate your addresses for those arrays, and essentially under the hood all these are just flat 1D arrays, so it works out kind of nice. What I want is a scalar, not a vector, scalar 2D index. So what you do is you pass in those same ij, ivar, il, and then you just need to pass in the size of these guys, and boom, you've got solution. So what I'll go ahead and do here is get rid of these this percents. Whoops. Let's fix that. Bam, gone. And let's go ahead and get rid of the interior host data stuff. Interior, host data. Let's go ahead and get rid of those. All right, so let's do this. Now we got VE2D index. Let's go ahead and dupe that. So just doing a little cheating here to get things to work. So I've got I also need to pass in a D matrix. I can't just use the DG matrix. What I need is a D matrix. So I'll make sure I get that added to the interface down below. Okay. And let's see here. Get rid of that. I want II times I, so it'll be II plus I times n plus 1. Cool. Yeah, and again, you know, if you start programming with self, using it for any of your projects, you'll start to get very familiar with these patterns. I try to keep it consistent throughout the code, so you're not having to reinvent the wheel every single time. Again, part of trying to keep things organized. All right, so let's finish cleaning this up. And var, close those brackets. And var, close those brackets. All right, so I've got that. And I've got the D matrix there. So let's go ahead and just pull that up for neatness sake. I guess that's subjective. And let's do the other one. And var. Okay. That looks good. Get rid of these line continuation parameters. Don't need those. So this guy, the D matrix, is II plus j times n plus 1. All right. So again, we got the velocity. Go ahead and steal from above. Oh, I already see a mistake in my Fortran code. I've got the wrong index there for the velocity. Should be 2, so I need to go back and fix that in the Fortran code. That would definitely have shown up as a correctness bug in some of our tests. So, but I guess it's kind of nice when you have to kind of duplicatively do this kind of work. You are able to catch some of these errors elsewhere. I suppose that's not so bad. All right, so let's get rid of that, and then we'll move that D matrix up. All right, now we've got our closing parentheses. Let's close that line. That was a doozy. I'm sure I made a mistake somewhere. We'll let the compiler tell us. But so I need to add D matrix next to the DG matrix. So again, I'll turn myself off here so I can see the code, and so you can see the code. Okay, so I got D matrix, B matrix, Q weights, F, solution, velocity, BF. All right, so now what we're going to do is we need to write the interface. So we're getting there. So we're going to copy that Flux Divergence interface there. Let's go back into self-advection. And let's create an interface. I'm going to keep that. I'm going to borrow again from self-Lagrange. Vector divergence, there we go. Vector DG divergence. That's the one we want to borrow from. 1, 2, 3, 4, 5, 6, 7, 8. All right, so I'm going to borrow that interface. We're going to change the name. Split form. Okay. Again, we got DG matrix, dev. I'm going to do D matrix, dev next to it. I've got B matrix, then Q weights, then F, then solution, then velocity. So I'll do it as sdev, vdev. That'll work. Let's go ahead and add those down here. Sdev, vdev. Let's add that D matrix. Okay. And then let's get that name right again. Okay, so now that we've got the interface, so boy, that's a long line. I'll have to clean that up. There we go. That's a little bit better. I knew that didn't look right. Okay, so if you followed what happened there, so what we did, right, is we defined a CPU kernel. And then we wanted to implement it on the GPU, so what we had to do was go into the corresponding C++ file underneath the HIP directory. So let's go there real quick so you summarize what happened. We created a kernel, a global subroutine in C++ so that it can be launched on the GPU. We implemented the method we wanted, using some of the syntax necessary to expose parallelism on the GPU. Down below, we implement a wrapper that essentially launches that kernel in C++, and we expose this wrapper to the Fortran interface. So now what we can do is essentially call that subroutine. So again, let's go back into that Lagrange class because we're borrowing so much from there. What I want to look for is vector DG divergence 2D GPU wrapper, because essentially we're going to steal the call syntax from there, so we can just, you know, use that in our higher level routine. So we got this guy. We're going to dupe that and bring it into here. Let's go down into our Flux Divergence. There we are. We're going to do a couple things. So if you remember, the model class has a GPU acceleration parameter attached to it. So if this %GPU accel, this is the attribute that's stored in the model that someone can change at runtime to toggle on or off GPU acceleration. Don't worry, that interface to enable GPU acceleration won't be set by that setter routine if a GPU is not detected on the system. So I mean, right now, I suppose someone could try to directly set that GPU accel parameter. This is why open source code is use at your own risk, I guess. That's all I got. So anyways, we're going to go ahead and bring that. Go ahead and indent some things. Let's put an else there. So basically, if we're not GPU accelerated, we're going to go ahead and run the CPU side. Okay, and let's put an end if there so we don't forget. Oh, and while I'm here, let me fix that velocity. Go ahead and turn myself back on because I don't think, yeah. Try to keep the code far enough away here. All right, so I got the velocity I messed up in here. That velocity component needs to be the second one. Great. Whew. All right. That's fixed. Let's get this guy fixed. So what's the name of that interface? This is how you know you're getting tired. Flux Divergence. And it's Flux Divergence, advection, 2D, split form, GPU wrapper. Now again, those my polys. What we want to do is replace them with this solution interp. We also need to have a, and you'll notice in this case, instead of using the host data attribute at the very end, I'm using device data. And this is, again, to make sure we're passing device pointers, so things that are allocated on the GPU to these interfaces. I also want to pass through is that D matrix. Now I've got, so fdev is going to be flux percent interior, right? Percent device data. And let's go take a look at that interface and make sure I get the ordering right here. Okay, so after f, I've got the solution, then the velocity vector, then the boundary normal. Okay. Well, I'm just going to go ahead and copy this down so I don't need to remember that. Okay, so we got flux, and then after flux, we've got solution. Whoops. So let's do this. Let's do this. All right, now I need the boundary flux. So at the boundary normal flux, remember, got to do that. So let's grab this guy, and let's change the interior to boundary normal. So, and then we need the flux divergence. Okay, almost there. So right now, all right, and I need n variables and n elements. So I need this percent solution. I need the number of variables, and then we need the number of elements. We can just pull those off the solution attributes. So that's it. That's let's see what I broke. That's always the next step. Now, oh, I'm in the wrong directory. There we go. All right. So now that let's assume we've got this done. I went through a little bit of refactoring so that I could get to basically using these pointer attributes for the interpolance, domain decomposition, etc. So I've got a few more things to add in here. So like the Riemann Solver and stuff needs to be implemented. Uh-oh. Usually when it vomits like this, there's something way up at the top that it's messed up. I've got a typo, expected label. Let's go fix that. An end subroutine. Yeah, so 46. Yeah, that's way up at the top. Didn't even get to the... you know what? I'm just going to do this. I'm just curious to see what I messed up here because something's not lining up, is it? Yeah, I got 2D written in there twice, of course. All right, let's give that another go. While that's building, I want to show you kind of how this ends up working when you write a program. So at some point, I'm going to get this merged into develop and then into main here in the next couple days. But there's going to be an examples directory that is going to have different models implemented with some of the tools that are, some of the library components that are implemented in source. And this kind of walks you through how you would set up a program to solve a specific PDE with your own set of boundary conditions and your own mesh, all this stuff. Eventually what I'll be doing is making some more robust programs with a complete command line interface, all these things for doing, I'm particularly interested in doing compressible seawater, so that's where I'll be going. But for those of you who out there who might have your own problem you want to solve, this is kind of the gist of how it would be done. is what you do. Usually is initialize the decomposition. Even if you're doing serial, the code builds actually with MPI libraries and everything active. And depending on whether or not you set the domain decomposition with MPI enabled determines whether or not MPI is initialized. And this is more of a dynamic way of enabling MPI. I know it's kind of unsafe because really you also need to make sure that if you set this to true, you're launching with MPI run. So there's some little details there I'm working on how to make that a little bit safer. But create a decomp. You can create an interpolant. There are some choices for the quadrature that are predefined. Again, documentation's coming very, very soon to tell you what all the options are. You can create a mesh. There are some inbuilt mesh generators. Now they don't have good element ordering, so they don't scale very well with MPI. And in fact, I don't recommend using uniform block mesh with MPI at all. Highly recommend using a tool like Hopper, the higher order preprocessor, or a mesh generator like Coke Mesh to get a decent mesh. And then I'm working on some tools that use graph theory to reorder the elements so that elements are ordered along spatial filling curves, so you can pre-process 2D meshes. Hopper only works with 3D. So anywho, that's that. Once you have your mesh, you have your decomp initialized, your interpolant, you can generate a decomposition. Now here, since we don't have MPI initialized, it essentially just says, okay, rank 1, you're getting everything. But you do need to do that. You generate some geometry. Once you have a mesh, this routine essentially will go through all the elements and figure out what the metric terms are. You initialize your model, and this is where you pass in the mesh, the geometry, the decomposition. And in this phase, since we're using pointers to reference, what interpolant to use, essentially the solutions are going to end up with the same interpolant that's used for the geometry. And this way, you're always guaranteeing that you're doing isoparametric modeling. At some point, I guess if it's requested, I could do things to make this more flexible, so you could do things like over integration. But for now, this is what we got. Just an example, if you wanted to set the solution name, here you could also do something like set the description of that object. The idea being that eventually what I'm getting to is offloading. This is some die, and then the units. The basic idea here is what you could do. Let's say, really concentrations are unitless, but let's call it kilogram per kilogram, something like that, right? Eventually, the idea is to take this metadata that you would set and inject it into the HDF5 output. So what I want to do ultimately is get a plugin written for pair review, for visit, some of these other tools so you can just work with those HDF5 output natively. We also have TechPlot output that will, again, I'm still working on getting the metadata stuff integrated into there. But the idea is you could set your solution information there. Now, if you want to enable GPU acceleration, again, you can call that this enable layer. It checks for a GPU if you have one. If you have one, it will make sure that all the routines underneath the hood call GPU on the GPU side. And of course, when you go to do file IO, it makes sure it copies back to the host side. So again, you don't have to worry about that. This is like all that complexity is really designed to try to get you to this point. Now, if you want to set the velocity field, of course, you can. I do have options to set different variables through files. Totally acceptable. One neat way, if you're trying to do like idealized modeling, you can use equations. So here I've just got a char array or a character array in Fortran for the velocity field. So here I'm just doing something simple, but then you can set the velocity field using that equation. So underneath the hood, right, this goes into FEQ parse, creates the equation parser, and then it will loop over the grid and actually evaluate that function that you put in there. So like if I wanted to be fancy with it, right, I could, I don't know, you get the idea. I mean, you can use basically predefined, you can use X, Y, Z, and T as your independent variables, fill in your functions. The initial condition, same thing. You could set it with a string, attach it to the solution. Here's how you write your HDF5 file, write your TechPlot file for initial conditions. I'm working on building out multiple time integrators right now. Euler and RK3 are supported. We got a few more coming, so hang tight. But you set your time integrator, set your time step. I have in my docket somewhere for later this year to do adaptive time stepping, so you can set an initial time step and let the model choose based off of a CFL function that you might be able to program, so that it knows how to adjust that time step. A couple more things are coming. So as you can see, I'm still working on figuring out how to set the formulation type that you want to use so that you could either use the conservative form that we had before or that split form that we just implemented today. And again, that's going to be model dependent, right? Those won't always be available for every single model. Then you just call forward step. You tell it, okay, I've got my initial time is at t. I tell it what I want to go up to, which is this tn value, and then you can write your file IO. I'll be adding some stuff, so like if you have, if you want to integrate basically from 0 to 100 seconds and then output every 10 seconds in between, well, I'll be adding some stuff there. Take care of that. But that's how it all comes together. So the programs in the end are very composable, which is something that I hear is very attractive about other languages like Julia. I'm hoping that folks see that you can get that kind of functionality out of Fortran. You just got to know how to use the OO features of Fortran. It's all doable. Let's take a look at our build. Probably still have some broken things, but not too bad. Missing actual argument for NL. Let's take a look there. 138. All right, let's take a look at our interface. All right, so I'm just going to go through this one by one. So I got DG matrix, yep. D matrix, yep. B matrix, yep. Q8s, yep. Flux, yes. Solution, yes. V, yep. BF, yep. DF, yep. I'm missing the interpolant degree. Damn, that's not too bad. I'll take that. Build it again. Yeah, and if you have any questions, feel free to reach out in the comments here now. If you want the GitHub repo where all this is done, let me see if I can add that. So the GitHub repo, go ahead and put that in the chat. So right now it's hosted by Fluid Numeric because right now I'm the only contributor, but as this grows, I do have hopes of getting this out into more of a community organization on GitHub. So definitely if you guys are interested in building conservation law solvers, you could start there. All right, let's figure out what's going on here. Undefined reference to. All right, let me make sure I got all my spelling right, because this is just going to be another spelling error, I think. So this is 139. Yep, that's this line. So again, let's grab that. That looks okay. suppose this is the other one that could be a problem, and then what I'll do is make sure in the hip module That's interesting. See if that did anything just by swapping those out. Looks like we resolved it. Must have been a typo. Let's make sure it gets to the C++ files. It looks like it did. It's building the library. Ah, yep, there we go. Oh, this might be the, I gotta check. All right, so the other thing here I did not show you yet is how to modify the make system to make sure you're including the files. That maybe that's what's going on. We got an undefined reference, so that'd be my guess. Let's take a look at the make file. So if you look, there's a few files for the make system. There's makefile, which kind of houses it all. We got make.include. Ignore that mason.build. I am working on a mason build system, but make.include, make.dependencies, make.compiler. Make.include is the one that is our workhorse here. It tells us all the things that it's going to build. So just make sure we got in the CPP sources. Yep, we're missing it. We need self-advection 2D. That would do it. So let's do this again. So yeah, you know, if you add a new C++ file, you end up just basically needing to add that to the CPP sources list and make that include. Again, while that's building, let's hop in there. Okay. As you add hip modules, you essentially just come in here and you'll add those to the list without the extension, because basically down below there's just some pattern logic in there that determines how, you know, what's the name of the .o that's created, If you've written make files, you kind of know where this is going. If you add examples underneath the examples directory, again, you'll just list them up here in the self examples variable. Right, it's just so those all get compiled. And eventually anything in this examples list gets integrated into the testing suite to run. So I will be adding some stuff to make sure you have ways to throw errors or do assertion checking, so you can actually do correctness checking and all that stuff. So let's take a look at how we did. Cool. Got some stuff that's not matching up. So solution velocity and velocit are undefined. Cool. So I got some issues with the argument ordering. So again, turn myself off so I can see here. So we got DG matrix. All right. So first, let's fix this velocit issue. That's an easy one. Oh, I did not add those to the interface. That would be why. So what's it? It was F, then solution, then velocity. Okay. So let's do that. F. Give that another go. Almost done here. Basically, once this is done, I'll go ahead and throw this up on my feature branch. And then in between now and the next 2 weeks, I'll be getting the correctness stuff done, and we'll move on to shallow water equations in a couple weeks. I will say, if you find these tutorials useful and you really want to dive in a little bit deeper, check out that Open Collective page that's referenced in the description. As I do have links posted over at the Open Collective page to some notes that accompany each of these live streaming sessions. So you'll have all the references I mentioned today, You'll have some work through notes that like go from the model, the mathematical model, to the discrete model and to the algorithm that we ultimately implement. I'm working on building out more stuff on the Riemann solvers in there, so there's a good deal to help you get started. So if you're building out your own models, I know I've been talking with some of you out there about doing multi-phase Navier-Stokes. A lot of the stuff I'm building here provides the foundation to help you be able to build out those kinds of complex models. Don't be afraid to get started. Certainly, if you were to start implementing a model and you reached out with a pull request, an issue, whatever, I'm here to help. So yeah, looks like we actually did good. The build went through, so I'm gonna go ahead and get this committed. And yeah, my file system might be full. Yeah, that's the other downside of Docker containers. Holy crap, yeah. I filled myself up here. I'll go ahead and get that fixed. Clean out some of these Docker images. So let's go ahead and do that now. So let's do a Docker prune. All right. Goodness gracious. All right, I'll go ahead and get that fixed here, but anyways, thanks all of you for joining. Keep an eye on our Open Collective on LinkedIn, wherever you found out about us. We'll be posting stuff here in about 2 weeks. We'll be doing shallow water equations next, so something a little bit more complex than advection, which will be fun. With those methods, we'll also be looking at a similar split form method to help maintain stability. And I'll have plenty of references coming your way, lots of paper reading between now and then. So thanks again for joining, guys, and I will see you in a couple weeks.